So let's work on the problem never wait for waits. As a reminder of the statement, you're given n variables and m operations, which can be either queries or updates. An update tells you the difference between two variables. For example, it may tell you that a minus b equals 5. And a second update might tell you that a minus c equals 3, for example. And then a query asks you for the difference between two variables. For example, it might ask you for the difference between b and c. All right. So for each query, we may either answer that the query is impossible to answer, which means we weren't given enough information to tell the difference between two variables, or we may need to give, if that's not the case, we need to give the difference between the two variables. In problems in which there is an impossible situation, it's often useful to start thinking about when that is the case, or when are you actually able to answer the query and when you aren't. So that may lead us into a way of representing this information we were given, because we need to answer queries in an online form, right? We're given queries and updates, and we progressively need to build a data structure which allows we to answer these queries efficiently. So let's try to build a data structure in which we can just know if we have enough information in order to respond a query, or if we don't. So when are we impossible? When are we not able to tell the difference between two variables? So in this case, we know that the difference between a and b is equal to 5, which means that if we know the difference between a and another variable, for example c in this case, this gives us the power to tell the difference between b and this other variable too, because of the laws of number theory, right? By simply manipulating equations, we may here derive the difference between b and c. And if we get to know the difference between c and yet another variable, again by transitivity, by manipulating simple equations, we are able to tell the difference between b and this other variable. Look, what these pieces of information we are given tell us is the relation between two variables. And what data structure actually represents relations between pairs of objects? It's a graph, right? A graph has nodes, which represent objects, and edges, which represent connections between two objects. So in this case, we could, for example, have a node for the variable a and a node for the variable b, and a number, a weight on the edge, which telling us the difference between, let's say, the variable with the highest lexicographical name and minus the value of the variable with the lowest lexicographical name. So in this case, this edge tells us the difference between a and b, and this edge would tell us the difference between a and c, which happens to be 3. So if we get to know the difference between c and, let's say, a variable d, which is here, or c and a variable e, which is represented by this node. If we're given this information, let's put some numbers here, we know that we are able to tell the difference between any pair of variables which are in the same connected component. On the other hand, if we have another variable f here, for instance, which has its connections but is otherwise disconnected from this set of variables, we cannot tell the difference between any of these variables and f. We simply weren't given enough information for that. So what we need to know in order to know if you are able to answer a query or not is to know if the pair of variables in the query belong to the same connected component. In this graph we can form by linking together nodes which represent variables by edges when we're given information about the difference between two nodes. So if we're given, for example, the question, what is the difference between C and C minus F? What is C minus F? Are we able to solve that? Well, in this case we're not, because C and F are indifferent connected components. Whereas, if the question was, what is the difference between D and E? Well, in this case we do have enough information to answer that, because we know the difference between C and D and the difference between C and E. And that gives us enough information. So, what data structure allows us to efficiently answer queries of the type, are these two nodes in the same connected components, while also allowing us to dynamically add edges to this graph? Well, it turns out to be the union-find data structure. Union-find allows us to create sets incrementally by linking together, by merging together two sets, which is what happens when you add an edge to a graph. If the nodes belong to different connected components, you just merged the two components into a single one. Whereas if they were already in the same component, then nothing happens. And in this problem, you already know that the information that will be given will always be consistent. So if we get an edge, if we receive an edge between B and C, we know that it won't contradict the information we already have, that the difference between B and C is 2 in this case. So if we happen to receive an edge here, we know that we can only receive one, which has a weight of 2. So a union-find data structure allows us to efficiently know if we are able to answer a query or not. So let's recap how union-find works, because it will be useful in this problem. So basically in union-find, what we have is actually a tree, a forest with one tree for each of the sets we're representing. And when we receive an update, when we want to merge two sets together, that is, when we want to for example, when we receive an edge, when we receive an edge, it represents the difference between two variables. And we have here a node between the two variables. We look for the representative node in each of the variables components. So in this initial case, in the initial state, each variable is its own representative, because each one is in its own connected component, in an isolated component. So to know if two variables are in different components, we just compare the representative nodes of the two components. If they're different, then they're different. They're in different components. If they're equal, they're in the same component. So after testing that, if we want to merge the two sets together, we basically need to make the representative node of one of the sets the parent of the other. So in this case, we might, for example, say that B is the parent of A. And then if we want to merge with this other edge, if we want to add this other edge to our data structure, we may find the parent of A, which happens to be B, and then find the parent of C, which is C itself, and then make one of them the parent of the other. So we may either say that B is the parent of C or C is the parent of B. It doesn't matter. And there are some optimizations you can apply to union-find. For example, if we are querying for the parent of A, and we'll eventually find it C, we may then put a direct pointer from A to C instead of passing through B, so that queries from A will be faster in the future. But you can note that we can augment this data structure with more information in such a way that we always know the difference between a certain node and the representative node of that node's component. So for instance, if we know that to get to the value of A, from the value of A to the value of B, because A minus B equals 5 in this case, we need to subtract 5 from A. So here we could put a value of minus 5. And since we know that the difference between oh sorry, here the edge should represent b minus c, so this is minus 2. So if we know that the difference, that b, to get to b, from b to c, we need to add 2, then when we are querying for the difference between a and its representative node, or a minus c in this case, we simply need to add the weights of the edges in the path from a to c. So in this case it would be 3, minus 3. To get from a to c, we just need to subtract 3, which is consistent with the information we were given here. So suppose we have then this union-find data structure, which allows us to efficiently know the difference between a node and its representative node. How does that solve our problem? Well, it does help because suppose we have like a certain tree here representing some connected component, each node representing a variable, and we have another different tree in this side. And suppose we're given then the difference between these two nodes. Let's say that this is the representative node of this component, and this root is the representative node of this other component. Suppose we're given the difference between this pair of nodes. Well, because we know the difference between this node and its representative efficiently, it's easy to calculate the difference between this node and this representative directly. But in the same way, because we know the difference between this guy and its representative, we may easily calculate the difference between the two representatives. It's just a matter of manipulating the information we have. So because of that, we may update our data structure by calculating the weight of the edge that should go between the two representatives and making it a single connected component. So we have enough information to put a weight on this edge. And if we're given a query between, for example, this node and this node, let's say we're given a query between these two nodes, how can we answer that? Well, it's easy because our structure guarantees that we can efficiently find, given that they are in the same component, we can efficiently find the difference between this node and a certain representative, which happens to be the same representative as this other node. So we know the difference between this node and this node, and between this node and this node. And obviously that allows us to calculate the difference between the two nodes we are interested in. So by augmenting the union-find data structure, we can actually guarantee that all these operations are efficient because we're not adding more complexity to our data structure. Basically, all the queries we used to do in the union-find data structure of finding the representative are maybe augmented with an operation of summing together the weights of the edges we encounter, by the way. But that doesn't make the complexity worse. And also, the optimizations that we could apply to the union-find data structure are equally applicable here. For example, the path compression optimization, in which we put direct pointers when we make queries. When we query this node, and we find out that its representative is this node, we can then update the parent pointer from all the nodes in the path directly to here. So we may erase this edge, erase this edge, and put direct edges here. All these optimizations are equally applicable because we can easily calculate the new weights of the edges that we'll put. And also the optimizations that guarantees that the structure is balanced, which is when we are about to merge two sets, we make the largest set the parent of the smallest set and not the opposite. This optimization is also applicable because the difference we put here is always a difference between, is always like the parent minus the child and we know the difference in both ways because it's like we can easily calculate b minus a from here. It's minus 5, right? You just need to invert the sign here. So it's arbitrary which node we put as a parent. And because of that, we can put any of them, and we can also apply that optimization. So that guarantees that with this augmented unified data structure, we can do all the operations we need. To tell if we are able to, when we are given a query, what is the difference between two variables, we first need to tell if we are able to answer that query. And that's just a traditional unified query. You just compare the two representatives of the two nodes of interest. If they are the same, then we are able to answer the query. Otherwise, we are not. If they are the same, then we just need to find the difference between both nodes and the same representative, and then use that information to calculate the difference between the two nodes themselves. And when we are given an extra piece of information, which is the difference between two variables, we first compare if they are in the same connected component. If they are, we don't need to do anything because we know that the information we're given is consistent. If they are not, then we find their representatives. We find both representatives, like in this case, and we calculate the difference between the two representatives using the information we have, and then we merge the two sets, just like we would do in a normal unified, but keeping this extra information in the edges. So because of that, we're able to solve this problem in all of m, which is the number of operations, times either log n or inverse Sackermann function of n, depending on whether you applied the optimizations, whether you applied both optimizations of the unified data structure or just one of them. And that's obviously efficient enough for this problem. That won't put us into any trouble, and we don't need to optimize further. So that's the solution to the problem, never wait for weights.